So I'll hand over to Peter. Any questions, I'm sure he'll be happy to answer as well. Okay.
Great. Well, good morning, everyone. As you've heard, my name's Peter. I work for the Centre for Clinical Success. I wouldn't exactly call myself an expert in statistics. Maybe, fairly knowledgeable. I cover it. Yeah, my background's more with mathematics and with research, in educational research, that sort of thing. So I've only got into statistics in the last 2-3 years. Well, more, it is. So we're going to run 3 sessions, as Paul has said. Today is an introductory one, as the title suggests. Next week, Maggie Gibson is going to talk about what's called descriptive statistics. And then the 3rd session, I'm going to talk about statistical testing, or it can be viewed as part of the quantitative data analysis process, because you should never really do testing on its own. You should always do descriptives first before you test. There is a 3rd kind of statistics we're not covering, which is becoming more popular, which is to do with what they call big data, or studying entire populations of data, rather than a lot of what we do is based on the assumption of taking a sample from a population. But I'm going to talk about that in a minute anyway. So it's going to be quite interactive, this session. There's a few things I want you to do, and I may need to edit some slides as I'm going along with the actual data that you collect this morning. So let's get going, shall we? So what we're going to cover is definition of statistics, then we'll look at statistical thinking, then I've got an experiment for you to do, then we'll look at descriptive statistics, which is just an introduction for next week, then probability theory, and then statistical inference, or statistical testing is another name for it. Okay, well, let's start with you. Perhaps you could take out a piece of paper if you still use such old-fashioned devices, or maybe write something on an electronic notepad if you've got one. So write down a definition of statistics and then discuss it with your neighbour. Agree between you, and then we'll just have a feedback to see what people think statistics is. I've given you a few clues already if you will listen. Okay, have you all managed to write something down? If you can pair up and share what you've put, and then try and agree between you and your pairs. Even threes, I don't know. Trends. Outlines change.
Not all size is about as vague as I could. So many things you can.
What do you mean by information?
Well, I avoided using the word data.
How is this different from quality? Research. Use some words which apply. quantitative.
Oh, yeah, I think quantitative is a good point, I think the reason I avoid data is that it tends to suggest that it has to be variable data, whereas I guess actually it's just, yeah, I think quantitative data.
Good. Sounds all right.
Yeah, it's one of the things is because we do a lot of data journals, a lot of work with data, but statistics, like that data might include textual data, interviews and so on. So I always,
Yeah, this is one of the misconceptions is that statistics is the same as data, whereas there's summary statistics, which is you derive those from data. So they're quite simple, and then you start to reason about summary statistics. To frequencies, well, if they were randomly selected, can you say it was unlikely that they would be so different?
We don't have to write it down.
It's very different from maths because it's about proving it. It's more than a thought, making judgments with beyond reasonable doubt.
Yeah, I think that's the difficulty from it is that it's literally being used in so many different ways.
Like these high profile sex offence cases where these guys get acquitted. And, in a sense, that means they can pronounce their innocence publicly. But it doesn't mean that there wasn't any evidence against them. It just means the evidence wasn't strong enough.
Yeah.
It's quite a high level.
That's the idea of the collection.
Misconception.
Collection.
Anyway, shall we pull these people together?
Yes.
Okay, if I could just draw your conversations to a conclusion, please. And have you managed to come to some kind of agreement between you? We've got 3 groups. You should share what you have come up with. So, what is statistics? Look at this first group.
I think we kind of broke it down into 3 stages. The collection, data measurement, and then drawing meaningful conclusions.
So there's a collection of data.
Yeah.
Yes. Data measurement, and the third one is drawing conclusions.
Yeah.
Okay, that's really nice. I think that covers a lot. And thank you. The next group.
There is sort of saying it's like quantitative data which can be like analysed to show trends and stuff. Like the main thing that we focused on was like finding outcomes of like the information that we're given.
So quantitative data which can be analysed
Yeah.
to show
Yeah, like trends and patterns and things.
trends and patterns. That's interesting.
To help kind of explain something.
To help
Yeah.
explain situations. That's very good work. Okay. Thank you. Lovely. And the third group.
Statistics is the analysis of data to provide meaning.
Analysis of data to provide
Meaning.
meaning. Oh, yes, that's very nice. Let's just try and do a little bit of qualitative analysis with your definitions. Let's see what we've got here. We've got the word data in all 3, haven't we? So it's something to do with data. Two of them mention analysis. So you're looking at the data in detail and doing something with it. And then there's an issue to do with interpretation. So you've got the word conclusions, meaning, and explain. So they seem to be three themes that you've come up with in your definitions. Okay, that's brilliant.
I'll show you what I've got here. The word statistics, it's commonly used in three different ways. There's a common meaning which is factual information involving numbers. So this is sometimes kind of a misuse of the word statistics in the media. Sorry, I'm not saying you're responsible, or will be. But a better word for this might be just the word data. Then there's a precise meaning, which is what we call summary statistics. So these are something which are derived from sample data. I've introduced the word sample there. I was talking about sampling earlier in populations, but we'll cover that more in a bit. So it could be the mean, or you might know it as average of a data set, so something that could be measured. So it could be, for us here, it could be what? Our heights in centimeters, and we could then take the mean of those heights. So that would be a statistic, or a summary statistic. And then another common meaning is an academic subject which involves the reasoning about statistical quantities. So we start with data, move to, maybe I should put this on over here. As you've said, start with data, then move to summary statistics, or some kind of quantity. I don't know if you can read this. And then from there, you're going to reason about it, which I think it's quite similar to what you put, because all of you mentioned data, and two of the groups mentioned analysis, so that's similar to what I'm calling the quantities. So maybe this is a more specific way of how you analyze data, when you create summary statistics, one thing you do, or some kind of quantity. And then from there, you do the reasoning. So you're talking about conclusions, explanations, meaning. Well, the reasoning is the process by which you obtain that. Are we together? Are you happy with that so far? Right. Well, so in order to use statistics properly, you need to be able to think about statistics in the right way. And it's quite different from mathematics, as I was just saying to Paul. Mathematics is about proving things. And there is no doubt, you know, like 1 and 1 is 2. It's just something which is true. Other things take steps to prove in mathematics, but they're all either 100% true or they're 100% false. But in statistics, it's not the same way of thinking. It's to do with, certainly in terms of the reasoning, it's to do with a modelling process, first of all, and secondly, it's not to do with proving anything. It's to do with making decisions with a certain level of confidence. So that's what statistical reasoning is about. Okay, so here's a little guide to the process. I think we will give you these slides anyway. They are available on iCity, I think, from that link at the bottom, if you can get to it. So I don't feel you have to copy everything down. So the statistical thinking process This is the modelling process. So it starts with a research question. It's very important that you identify what it is you are looking into. And it's not to say you have to follow that exactly as you go through the research process, but it kind of guides you in terms of what you're doing. So when you've done that, it's about either using somebody else's data which you understand how it was obtained, or you obtain your data in the best way. So once you've got the data, you're into the descriptive stage. So it's about presenting it and informally describing it. So it's things like the summary statistics I've talked about. It could be charts, frequency charts, tables, or it could be charts such as a bar chart or a histogram, the sort of thing Maggie's going to talk about in more detail next week. So when you've done that, you start to informally interpret what you have and look for features. And maybe it's like a combination of your research questions and the features you identify in the data. You start to home in on something that you want to analyze in more detail. So that leads you into the statistical testing phase. So it's about selecting and carrying out the appropriate test. Then you've got to interpret or draw a conclusion from that test. But that's not the end of it, because it's a modelling process. You may find the way the test has been applied, you think, well, perhaps I can do this slightly differently or use a different test. You tend to kind of go around in a loop there from number 7, and you may need to refine what you're doing. So there isn't like one right answer for what a data set means or how you should interpret it, or even go about a study in a more general sense. So statistical thinking underlies quantitative research methods. So it's the underpinning capability. So having given those 3 definitions, I'll now mention 3 areas of statistics. And I did mention earlier there is a 4th one, which is this kind of big data population studies, which we're not going to cover. But these are the 3 I'm going to major on. Descriptive statistics, as I've said already, is something Maggie will go into more detail with next week. It's about describing and summarizing data sets using pictures and summary statistics. Inferential statistics or statistical testing is about analyzing data sets and drawing conclusions. And probability theory, it's interesting, one of the groups mentioned trends and patterns. This is where probability theory comes into play, because a lot of statistics is based around what's called distributions, and the most common one looks like this, the normal distribution. So this is a certain pattern you would look for in terms of the frequency of something occurring, such as the example I was giving earlier, the heights of people in the room. You might expect them to form a curve similar to this, although the sample's a bit small. So probability theory underpins a lot of inferential statistics. Let's leave it at that for the moment. I won't go into too much detail. So it's the study of chance events governed by rules. So we're going to look at that a bit today. Right, so inferential statistics, statistical testing is based on based on probability, because it often uses random samples of data drawn from a population. So obviously, people here are not a random sample of people in the university in one sense, because most of you are on the journalism course and you decided to come to this workshop, but in the sense of your heights, I can't see why you wouldn't be a random sample. You get the idea. So what do I mean by random samples and populations? Well, that's what this slide's about. Picture of groups of ants. So the population is all of them, so you can imagine all the ants in a colony, and then there'll be too many for you to study, so you study a sample of them. And what you find out about that sample enables you to say with sort of a high degree of confidence what is going on with the entire population. So a very common example is opinion polls. Opinion polls tend to interview maybe 2,000, 4,000 people, and they try to make sure that their sample is randomized, maybe in terms of the kind of the different demographics they come from, that sort of thing, or like the ages or the gender, the social economic background, that sort of thing, to make them representative. So you can't interview everyone in the country because it would cost too much money. But if you interview a few thousand, then you can say with a pretty high degree of confidence what 20, 30 million people are thinking. So that's the power of statistical inference. Are we all together still? I've got another activity for you in a minute. Here we go. I'm going to pose you a research question. Pretty silly one. If you stick a lump of blue tack to a coin, does it make it biased? Well, you'd think so, wouldn't you? But we're going to actually try it out. Okay. So I'd like you to, I've got some blue tack here, and I hope some of you are not too poor or too electronically minded with your money that you don't have a coin. So some of you got a coin, doesn't matter what coin. You can either work individually or in pairs. And what I'd like you to do is stick a lump of blue tack to a coin. I'm not saying what size coin or what size blue tack. The only thing I'm asking you to do is stick it to the head side of the coin. And toss the coin 20 times and record the number of heads and tails. Okay. Can I give out some blue tack? You don't? That's okay.
Thank you very much.
Right. Right, so toss it 20 times and record the number of heads and tails. Want to do it full? Yeah. We need to get a better test That's maybe not such a good idea. As I had, cameras capture it, helps it optimise as well. Okay, are you nearly there? If you finish, then there's a question at the bottom to consider. What ratio of heads to tails do you think would indicate your coin is biased? The bottom question. Would it have to be 20-0, 19-1? Are you nearly there? Yeah? Okay. I think I'm going to start taking in the results. I'm going to have to edit this. I'm not very good with PowerPoint, so give me a minute. Right. Okay, first group.
10.
Okay, so there were 10 heads.
Yes.
Okay. The next one.
11.
11 heads. Third group.
5.
5 heads. Okay.
14.
14.
Yeah.
Wow. Okay.
9.
9. Thank you.
10.
10.
9.
9.
12.
12.
11.
11.
It's 11. Sorry, 9 heads.
9 heads. Thank you very much. So how does that look to you? Normal?
No bias.
No bias. It looks pretty normal to me too. There was one pretty low one, the 5 one. Sometimes when I've done this, we've had a lot of extreme scores, so maybe it's the way you've been tossing the coin. I don't think it's such a random event that everyone's ended up with things in the middle. Anyway, it's a data set that we've got now. So this introduces... Right, the next subject, descriptive statistics. I've mentioned this briefly already. Well, 3 things: frequency tables, different kinds of chart, and summary statistics. I'm not going to cover everything here. I'm just going to give you a flavor and try to connect it with the data we've already collected. So, lesson 101 is what's called data types. It's a very important concept in statistics. You may not have thought about this. I certainly had forgotten about it when I retrained as a statistician. So there are 3 fundamental data types in statistics. Data called nominal, which is category based, and it does not have a natural order to it. So it's things like gender, eye color, and the experiment we've done, I think, would come into that category, heads and tails, because it's what's called binary data. Could be either way round. Secondly is ordinal data, which is also category based. So not all data in statistics is numerical. Some of the data you're counting frequencies of categories. The thing about ordinal data is it has a natural order to it. And the most common example is what's called the Likert response scale. I don't know if you've seen these. You get them all the time in questionnaires. So they go strongly, disagree, disagree, neutral, agree, strongly agree. So within that scale, you can't say that agree is anywhere else apart from where it is. It has to be in between strongly agree and neutral. You can't put it anywhere else. So it is an ordered scale. You have a natural order because of that. You could put it round the other way. You can flip it over, but it has a natural order. So it's different from nominal data. And I think next week, Maggie will give you a little exercise with descriptive statistics. I mean with data types. Scale data is the numerical one. So we call it scale data. It's things like weight, time, length, counting events, that sort of thing. Doesn't have to be what's called a real number with lots of decimal places. It can be a whole number, an integer. But it's measured against a constant scale. So the best data in statistics is scale data. The second best data is ordinal. The least good data is nominal. So if you start with scale data, you should try and keep it that way, unless you have to turn it into, like maybe interval categories, would turn it into ordinal data. So an example would be people's age. So you could measure age right down to dates of birth, or you could just give age as a year. Either of those would be a scale data type. But if you were to turn it into maybe decades, it would be turned into ordinal data. Some people are a bit embarrassed about giving their age in years, very understandable. So there is an ethical issue about, is it right to obtain the richest form of data in this situation? So you've got to balance that ethical issue against how useful it would be to do the analysis with the more rich data. Are you getting what I'm saying? Yeah? Good. Okay.
I'm curious what latitude and longitude would fall in that.
Latitude and longitude.
Yeah.
I think you would call them scale data because you could add them and subtract them. It would be meaningful. Whereas you can't with a Likert scale. The classic mistake with Likert scales is people turn them into numbers and then work out an average. And you shouldn't do that. Because how do you know strongly agree is twice as far from neutral as agree? It could be 1.5 times, it could be 10 times. It depends how you interpret the word. Whereas longitude, latitude are basically they're a scale, aren't they? Okay, so now we've got to fill in this table. So we've got to go back and look at what we had. It might be worth writing it on the board if I go back a few slides. Okay. We put them in ascending order. Then we got 5, 9, is it next?
Yeah, there's 3 9s.
3 9s?
Yeah.
Wow. 9, 9, 9.
2 10s.
2 10s, thank you.
2 11s.
2 11s.
1 12 and 1 14.
1 12, 1 14.
Have
we missed
No, that's group 8.
sorry.
Is that 10 numbers there? 4, 5, 6, 7, 8, 9, 10. Yeah, that should be it. But we can remember that. This is not a very good way of recording things, is it? I need your help. So now we can fill in the frequency. Yeah, sorry. Back here. So there were no zeros, no 1s, no 2s, no 3s. There was 1 4.
No.
No. 1 5. No 6s, no 7s, no 8s. 3 9s. 2 10s. 2 11s. How many 12s? 1 12, thank you. And was it 1 14?
Yeah.
And that was it. Okay. So that's the frequency table for the data we've had. So we've now counted the number according to the number of heads. So we've summarized the data a bit. And now we're going to turn it into interval frequencies. So we're going to, rather than have the individual heads values, we're collecting them together into an interval, an ordinal data group. So 0 to 2 there were none, 3 to 5 there was 1, 6 to 8, 0, that's interesting, 9 to 11, isn't it 8? Oh, you're right, 7, sorry, it's 12, isn't it? 12 to 14 there are 2, and then 0, 0. So that's the pattern we've got.
Now, unfortunately, my slides are not quite technical enough to turn this into a picture, but here's one I prepared earlier to use the BBC phrase, a histogram like that. So this is an example of a histogram. On the bottom, it's like a scale variable or intervals, and we've counted the number in each interval given by the height of the bar. And the difference between a bar chart and a histogram is you want to join them together in a histogram to represent the fact that the data is, in some sense, continuous along the horizontal axis. Okay?
Do they always have interval frequencies?
Yeah, I think so. Histograms do, yeah. Because you have to measure the frequency in each one.
But I mean, like, when you do it individually, is it?
Yeah, you could do it individually, but you wouldn't necessarily join the bars together. You could do, if you wanted. You could do either then. So here's a bar chart. This is the alternative. So this is the average number of passenger miles per person per year for various forms of transport. I don't know where the data came from. But you've got different forms of transport on the horizontal axis now. So there's no way that you could combine them together as intervals, or there wouldn't be any meaning of being halfway between a car and a bus. You get the point. So in Excel, it's you can create charts which look quite nice, but you can also, the default ones are quite horrible, to be honest, so you have to put some work into it, and that's another one of the workshops we do about how to create nice charts in Excel. They also run courses at CICT, but I don't know if they're so academic in their perspective. For example, we always recommend two-dimensional bar charts rather than these funky three-dimensional ones. I don't know how it is in journalism. Also, here the vertical axis, we always recommend starting from 0 rather than cutting it off, otherwise it's quite misleading. So two-dimensional bar charts are easier to read, so that's why we recommend that.
Yeah, we have.
Okay.
I do go on about
Okay.
It's a pet. 3D is a pet hair to me.
Oh, good. I'm so happy to hear that. So there are two kinds of summary statistic, measures of middle value and measures of spread. And again, Maggie will go into more detail next week about these. The three measures of middle value are called mean, mode, and median. And measures of spread, well, the two we put here are range and standard deviation. There is a third one called interquartile range. So I'm going to just apply those to the data we've collected and see what we end up with. So some of these we can calculate. Let's see what we can do. So the mean is what? What is the mean of the data set? Sometimes called the average.
A sum of individual.
Yes.
Divided by the number of terms.
Yes. So we could take these values, add them together, divide by 10. That would give us the mean. It's what's commonly known as the average. So what does that work out as? Can you? 3. It's 5 less than 8 less than 10, and 1, 2, 3, 4, 8 more. So it's exactly 10 for me. Right. What about mode? What is mode? Yes. So to remember what mode means, think about fashion. Mode and fashion. Mode is the most popular. So what of our data set? Yes.
It means 10.2.
Is it?
Yeah.
Oh. Thank you. 1, 2, 3, 4, 8. 1, 2, 3, 8.
It's 8. These are 8 less than 10 each, and these are 8 more. So I think it did. I think they add to 100.
Yeah, I think 203 grand. Well, I was counting ahead. 3 grand.
He says it's 10.
Okay, I'll go with that. I was going through it, I was just I don't in my head, but I can't do 3 grand.
Okay. Well, I added it up quickly by seeing which were less than 10 and which were more.
Okay.
But I appreciate people having an assertive attitude. So the mode. Mode is the most popular, so which is the most popular? 9. There were 3 9s, the others there were only 2 of. Some of them, and then 1 of. So 9 is the most popular. Okay, median. What is the median? Yes, it's the middle point when the numbers are written in ascending or descending order. So this is what we've done already. They go 5, 9, 9, 9, 10, 10, 11, 11, 12, 14. The problem is we've got an even number of values, because an even number of experiments took place. So there is 2 numbers in the middle, the 5th and the 6th number. So 1, 2, 3, 4. They're both 10. So generally speaking, if you've got an even number of values, you take the 2 values in the middle, add them together, divide by 2. But because they're the same, then the median is just 10. And finally, the range. You know what the range is?
9.
9. How did you calculate that?
That's the smallest. Like the smallest is smallest.
Yes. So it's the distance from the smallest to the biggest. So it's from 5 to 14. So the range is 9. Okay, so the range, it just happens to be the same number approximately as the measures of middle value. And you would expect if we did like 100 experiments, the range would increase and get nearer to the maximum theoretical range, which is 20. Okay, very good. So that's that. Right. So we now need to do a bit of probability theory. How many heads should we expect? So if a coin is unbiased, it doesn't have blue tack stuck to it, probability of tossing a head or a tail is a half. And it's not affected by the last toss, as long as you give it a good spin. So that means we can multiply the probabilities together. So for the individual events, for example, having a head, then a tail, then a head, you could just multiply together the probability of a head on its own, a tail on its own, and a head on its own. So the probability of having that sequence, head, tail, head, is a half times a half times a half, which is an eighth. Is everyone happy with that concept? Yeah? Just about. Whoa! Let me just make sure I'm going gently here. Okay, so that is a particular sequence, but there are different ways of getting 2 heads and 1 tail. And that's what I want to get onto. Or getting 3 heads. There's only one way of getting 3 heads. There's different ways of getting 1 head and 2 tails. Depends when you throw the head. It could be the first coin, the second coin, or the third coin. So this takes us into what's called decision trees. You might need to meditate on this a bit after the class. So in terms of 2 heads and a tail, there's 3 different ways of doing it. So either the tail comes at the beginning, which is when we come down this route, tail, then head, tail, head, head, or it comes in the middle,
So you do a head first, then a head, then a tail, then head, tail, head, or it's last. So it's head, another head, and then the tail. So there's 3 different branches on this tree. The probability of these events is both a half. The probability of these events, they're all equally likely, they're all a quarter. And then the probability of these is they're all an eighth. So the compound event of throwing 2 heads and 1 tail when you toss a coin 3 times is to add these together, because they're what's called exclusive events. They can't happen at the same time. So the events are independent and they're also exclusive. That means you can multiply repeated events and you can add the events you end up with when you've done the experiment several times, the possible outcomes. So adding together, you get 3 times an eighth, you get 3 eighths. Is that kind of, I'm still keeping you, most of you? Okay. Right, well that takes us into what's known as a probability distribution, which is based on what I've shown you. Now it's got the 4 different possibilities in terms of tossing a coin 3 times and the number of heads you might get. As I've already said, to get no heads you have to throw 3 tails. So the probability of that is a half times a half times a half, which is an eighth. The same for 3 heads. It's an eighth. And the ones in between, they are equivalent. It's either 2 heads and a tail or 2 tails and a head. You've got to throw the other one at 1 point, and then you know what the other 2 are. So it's 3 eighths. So if you add these together, you get 1. Because the sum of the probabilities has to be 1. This is all the possibilities in terms of measuring the number of heads when you toss a coin 3 times. So this graph is quite similar to the bar charts and histograms I was showing you earlier. The difference is on the vertical axis now we have probability rather than frequencies, or measuring number of miles or something. So you can see its shape is looking a bit like this picture I drew earlier of the normal distribution. And I'm not going to bore you with any theory, but when you repeat tossing a coin many times, the distribution turns into a normal distribution curve. Okay, and that's going to help us when we come to think about, well, were any of these events unlikely or not? Right. Right, so that takes us into statistical inference or decision making or testing, whatever you want to call it. The third stage, the third element of statistics, we talked about descriptives, talked a bit about probability theory. Now this is a statistical inference. So when we carry out an experiment, we measure the likelihood of the event which occurs and all other equally likely or less likely events. We then make a decision about whether the outcome was likely or unlikely based on the sum of these probabilities. And the decision is based upon these rules here. If the sum of probabilities is bigger than 0.05, we say the event was just a normal one. It's lower than our threshold. But if the sum of probabilities is less than 0.05, we say that was an unlikely event. So when we have an unlikely event, it's a bit like convicting a criminal beyond reasonable doubt. So the level of doubt in statistics is set at a standard level of 5%. Which is quite high, really, compared to the legal system. But that's what we use. We also have, we talk about 3 levels. So the 5% level, we call that evidence. And then the 1% is strong evidence. and the 0.1% is very strong evidence. So examples of this would be things like climate change and the Higgs boson. I don't know if you've seen how the stories have developed in the media, but climate change, I think, it's moved from sort of 5% level to a 1%, maybe a 0.1 in people's perception. And when all the academics have got together and they've looked at the entire evidence, they're now pretty sure it's to do with human intervention, that we have climate change. It's not just all the other factors impinging. Higgs boson, I think, is much higher than 0.1% in terms of strength. It's like 0.01. Sorry to talk about these numbers like round the wrong way, but that's how it is. Sometimes we reverse the probabilities and say 95%, 99%, 99.9. But you get the idea. So there is also something called the null hypothesis, and the alternative, we'll talk about that in the third week. Okay, two-tailed test, just a bit of a concept for you. If you don't suspect beforehand what kind of bias, like in our experiment, we didn't say we expected more heads or more tails, then you look at both, sorry to use the word tail twice, but you look at both ends of the distribution for the unlikely events. And this is the most common way of doing testing. This is what's called a two-tailed test. If you're only looking at one end, it means you have, beforehand, you have an idea of which way you expect the thing to go. And you're testing for that. Normally you test the opposite to see if it's false. So one-sided tests are much less common in statistics. Two-sided tests are the norm. So this is the good old normal distribution curve, and these are the tails, and they cover 5% of the area of the distribution. So 95% is in the middle. These are the events you would expect to happen most of the time. 5% of the area is in the tails. These are the unlikely events. Have you heard of the number 1.96? Have you studied statistics? Well, when you standardize this, it ends up as 1.96 times something else. But you may have heard of that number. But it doesn't matter for today. So with the example I was giving you, when you just toss a coin 3 times, what if you had 0 heads? Would that be an unlikely event in terms of what I've just explained? Well, in order to look at that, you would do a two-tailed test. So you would look at that event, you'd look at other events which were equally unlikely or even less likely. So there are no events which are less likely, but there is one which is equally unlikely, which is 3 heads and 0 tails. So that also has a probability of 1/8. So then you have to add them together, and you get the number 0.25. And that number is bigger than this threshold of 0.05. So you would say there is no evidence that the coin is biased if you just get 3 tails in a row or 3 heads in a row. But if you were to do 10 in a row, that might be different. Yeah? It's pretty strong evidence, I think, by the time you get to 10. Because the likelihood of that is about either 10 heads or 10 tails is about 1 in 500. So that's taking you down to this level. That's 1 in 100. It's going to be less than this one, that's 1 in 1,000. So you'd have strong evidence that the coin is biased if you ended up with 10 in a row. But we're not looking at that, we're looking at tossing a coin 20 times and getting a certain number of heads and tails, which is the experiment you did. Okay, so when you do that, you end up with a
probability distribution that looks like this. And as I've said already, it's looking more and more like a normal curve. So what you need to do is look at the tails and kind of move back from those until you get to a probability value when you add them all together, which is as near as possible to 5%. So it turns out that that occurs when you add 6 on the right and 6 on the left. So 0, 1, 2, 3, 4, and 5, and 15 up to 20. Add those probabilities together, you get the number 0.041. So that's less than 5%. Are you still following? Some of you. Okay. So what that means is, if you do one experiment and you end up with a result in either the left tail or the right tail, you would make the decision with 95% confidence that the coin is biased, which I think one of you had. But it's 1 out of 10 people in the group, isn't it? We did 10 experiments. Okay. So I've just said that. The trouble is, we're only using a 5% cut-off value for making our decision, and it could be a random event. So you would expect 1 in 20 decisions for the coin to be biased when the coin isn't biased. Imagine if we hadn't stuck BlueTack to it, we would still expect 1 out of 20 of these experiments to have come back with a biased decision. So we had 1 in 10 of the events, which isn't far out, really. So only 1 of our coins was decided as being biased, but because there were 10 experiments, that would be, you know, par for the course. I've done this with other groups, and we've done maybe 20, 30 experiments, and we've had a lot of them coming back as biased, which is showing you that at least some of the coins appear to be biased, because you've got more than the expected proportion of decisions from the individual experiments. So this is called type 1 error, when you decide a coin is biased when it isn't actually biased. You make a decision that something is an unlikely event when in fact it was just a random event. Okay, so I don't think I need to go through that because I've already explained that. We could just write out the number of heads and put the one with, was it 5? We put that one in red, and the rest of them we would just say they are normal events. Okay, finally, just some thoughts. Common errors in statistics, statistical analysis. Students come to us and say, here's my data set, I've got to hand this in tomorrow. What do I do with it? So that is not a very good situation to get yourself into. You need to plan ahead. What are the data types you have in your data set? What kind of analysis are you planning to? What is your research question? So you've got to have a better idea from the beginning. Secondly, a mismatch between your data types and the test you're using. So as I've mentioned already, Likert scales, people make the mistake of turning them into numbers and then pretending that they can do certain things with them. So what we recommend, instead of the normal strongly disagree to strongly agree Likert scale, is a scale like this. And there's a lot of thought has gone into this. It's only anchored at the ends with strongly disagree and strongly agree, and it has 7 numbers rather than 5. And 7 is ideal because of making the data a bit richer, but not overpowering people's what's called working memory. because there is working memory theory is people can only cope with about 7 plus or minus 2 pieces of information at any time. So what happens when you have more numbers here is people tend to choose a number at the left, or a number in the middle, or a number in the end, rather than distinguishing between all 7 numbers. And it's better to only anchor the ends, because then people are choosing a number in a scale rather than interpreting a word next to a number. So this is the best way to do Likert scales, and it means that you end up with scale-based data, and there are more possibilities for analysis if you happen to be doing questionnaires. Other mistakes we see is people just copy and paste the output from computer software and put it in their report, maybe without any commentary to go with it. It's about being selective with output. It's about interpreting it. You may want to put the output in an appendix, but don't just copy and paste it without any interpretation. And fourthly is the misuse of the word significant. So the word significant is about this cut-off level, the 95% or 99 or 99.9 level. It shouldn't be used in another context when you're dealing with quantitative data. Did you have a question?
Yeah, about the I've got my data, but I don't know what to do with it.
Right.
Sometimes the data comes to you
Yes.
and you don't know what to do with it.
Right.
And then you have to decide, and suddenly you get a feeling that you could use the data, but you don't
Right.
know how to use it.
Yes. So this is more kind of an explorative approach, and there are some techniques which support that. The problem is what I was talking about on the previous slide, the type 1 error. If you're looking at data without a research question in mind, and you maybe got different variables, you're maybe doing different charts, you suddenly see something, oh, that looks interesting. But you may have looked at 20 things, and one of them seems to have a feature, and then you do a test, and it comes back as positive. That is not good statistics, because you would expect 1 in 20 to have some kind of structure, feature to it as a random thing. So you have to be aware of that when you're exploring your data set. So there are techniques which can help with that process, which reduce the risk of making these type 1 errors. But that is valid, it's a valid point. Sometimes you're given big data sets, you're just exploring them. You don't have a particular research question in mind, but you have to be careful that you don't draw inappropriate conclusions based on your descriptive process. Okay? Yes?
So, like, what types of data normally subscribe to the normal distribution? Obviously, because that ties into what you just said. You know.
Or people's heights,
Yeah.
coin tosses.
Because if you get a piece of data and you don't know whether it's
Well, we're going to cover that in week 3,
Okay.
in lecture 3, because when we do the descriptive statistics, another more detailed thing I've not mentioned is assumption checking for the tests which are making the assumption data is coming from a distribution. So there are different distributions. We tend to deal with the normal distribution a lot of the time. But it's not necessarily the case. For example, if you're using these Likert scales, you need to test the data for a normal distribution for individual questions. But quite often people ask questions in a group, and then you can add the values together for all the questions in the group. The shape of the data then tends to smooth out a lot more when you do that. So we'll look at assumption checking in week 3. But there's only so much you can do in a package like Excel with assumption checking. You have to use a statistical package like SPSS. I think I mentioned that. Okay. swear word, isn't it? Actually, but we do run training in it, so and it's not too scary. Okay, I just wanted to show you some resources. We do have some online things. We've got a whole course on statistical methods. What I presented today is it's like a version of the first workshop in this course. Slightly different, but similar material. So there are 15 workshops on statistical methods on that link. Past is very nice. I'm going to be using that, I think, in week 3. It's Java-based applets which demonstrate statistical concepts based around real data sets, or actual data. So here we are. That's quite nice. Statistics glossary, if you're looking for the definition of concepts, that's quite good. And Stats Tutor is a repository of individual learning resources based at the University of Loughborough, and we've just donated about 30 resources to them, including this workshop. So they should be out in the next week or 2. There's a few books in the library. And then that's about it, really. What are we doing for time? Oh, that's good, actually. All right.
These slides will be available.
Yeah, I can.
I've already put them on Moodle with this.
Yeah.
Just sweet. And I'm just putting Stats Tutor on as well.
Okay, so just an evaluation sheet, unless there's any other questions.
And the most really just to head up, I want to do that, I have